This video is to introduce my electrical and computer engineering for S6 project. What am I doing is automatic belt driving system. The system uses 4 sensors to sensing force applied to a proposed area and send signal to the motors to drive the motors, and the signal is processing by a central controller board, and the motor will drive some telescopic arm mechanism to drive the belt and use the belt to lock the object loading on the proposed area. I have built a prototype for the system. Next, I will demonstrate the structure and operations of this prototype. Now the system just started up, and the sensors and the motors are locked until the power button is pressed, which is here. And see that green light is on, which means the power is on. And we can also go to the serial monitor, and it shows us the system power is on. As default, the system is on dual mode, which means sensor 1, which is this one, is driving both the two motors, and sensor 2 is on the idle state, which doesn't do anything at this time. Now let's press the sensor to apply some force. Just now, because we applied force to sensor 1, both the two motors and timing belts are driven automatically, which demonstrates how the future belts, which the actual belts, will be driven out and locked. And now the two belts is like theoretically locked, and we can also tell it from the serial monitor here. Because the two belts are both locked, so now the two motors should be at idle state, because there's no belt should driven by them. Therefore, the sensors are also idle at this moment. Let's try the first sensor. No matter how long I apply a significant force to it, it does nothing. And to unlock the belt, we can use the unlock button here. The two buttons, one for belt 1, one for belt 2. However, now it's the dual mode, so both belts are bonded together. So no matter which button you pull, I pressed, both the belts will be unlocked. Let's just randomly press one, and from the serial monitor tells us both the belts are unlocked. And now we apply some force to the sensor. See? Both the belts are driven again. That's it for the dual mode. Next, let's move to the single mode, which means each sensor control each different motors and belts. And to switch the mode, just press this button. And from the serial monitor, we can see now it's single mode. And now let's unlock the two belts and try sensor 1. Yeah, we see that only the first belt and the first motor are driven, and from the serial monitor, we see that only belt 1 locked this time. So now the sensor number 2 and the motor number 2 should be still available. And if I apply force to sensor number 2, we see that the motors driving again, and as before, now the valve number 2 should be locked. Now, no matter what I do to which sensor, nothing will happen because both the valves are locked and the system is like at idle state. And I think that's it for the whole overview. And there's only two modes, the dual mode and the single mode. Next, I will talk about the designs of the telescopic arms, which can be used in the real case for the system. I have two designs on the arms. The first one is based on the concept of conveyor belt. It would be built with multiple layers of conveyors. The outer layer can drive its inner layer in or out to achieve the functionality of telescopic arm. An important advantage of this design is it can drive the belt across a full circle, and since the belt can be tightened up mechanically, the system can tie up almost all shapes of solid objects without using any extra space. The second design is based on the concept of timing belt. Comparing to the first one, the second design is easier to be built because most parts can be purchased from the market instead of being individually manufactured. However, the final product will be much larger inside, and the whole system will use a significant amount of space. Partial of this design was built and implemented in this prototype. For the electric design, the central controller board for the prototype is just some low-end microcontroller with some customized buttons, pins, and motor interfaces. I haven't got any performance issues to control the two motors by now, and the full sensor are just some small full sensor resistors. Looking at the cost of the prototype, I can say that the real product of the automatic driving belt system will be low cost, and there's no high technology required, and which proves that it will be a cost-effective and efficient system. For the system orientations, the two modes of the prototype system have proved the system is capable to handle two kinds of orientations. In the real case application, the two situations can be combined together, and the coding for the real production will have the similar complexity as the orientation of multiple loading pads with a belt attached to each pad. On the software side, there will be a function for each loading pad, and the function will keep reading the signal from all the relevant input pins, use its own counter or timer to count the time, and write all different kinds of responses to all relevant output pins. For the real-world application of this automatic belt driving system, it can be adapted in many real-case situations. It can be used in automobile seatbelts to service the elders or disabled people. It can be used in aircraft seatbelts to achieve a higher safety level. It can be installed to wheelchairs to ensure better safety to the patients. It can be attached to roller coasters or other similar facilities to enhance the safety. There are also a wide range of industrial implementations. One example is transportation of vehicles for vehicle manufacturers. Driving a car to the loading pad, and it will be tied up. It becomes more stabilized, and the belt will not cause any scratch on the car. As a result, the automatic belt driving system is realistic and worth to be implemented. Because there is not any special requirement, and the system is cost effective and efficient.